When we use a large number of evenly spaced nodes to interpolate a function, the resulting interpolating polynomial may suffer from Runge's phenomenon. Typically, we want our polynomial to interpolate our function better or be a better approximation of a function if we choose more and more nodes, but that's not actually guaranteed. And so what I want to show you is these graphs. The function in blue is 1 divided by 25x squared plus 1, and then in orange, the orange curve is the interpolating polynomial with 5, 7, 9, 11 nodes. So with 5 nodes, it doesn't interpolate very well, right? We think, yeah, we definitely need more nodes so that this orange polynomial will approximate the blue curve better. So then we choose 7 nodes. And it's getting better around the middle, but it's actually getting worse around the edges. And then we choose 9 nodes, and it's getting pretty good around the middle, but it's getting really, really bad around the edges. And then again, when we choose 11 nodes, it's almost perfect around the middle of the interval, but around the ends of the interval, it's getting worse and worse, right? Every single time we're adding 2 more nodes, we're getting better convergence around the middle of the interval, but the endpoints are getting worse and worse and worse. So when we were talking about Newton-Cotes quadrature last time, we said, we're going to basically come up with a Lagrange interpolating polynomial based on evenly spaced nodes. We'll exactly integrate the interpolated polynomial, and that would be our approximation of the function. But this is saying that choosing a Newton-Cotes quadrature rule with more and more and more and more and more nodes is not going to always give you a better and better integral approximation the way we hoped it would. Obviously, if I take one Newton-Cotes quadrature rule, like if I just take the Simpson's rule and then I use more and more and more sub-intervals of Simpson's rule, that will converge. But if I just try to go from Simpson's rule, which is like a k plus 1 equals 3 nodes, to Boole's rule, which is like a k plus 1 equals 5 nodes, to 7 nodes, to 9 nodes, 11 nodes, that's not going to converge. So this is called Runge's phenomenon. The fact that like these maximum absolute errors at some point along the interval are actually growing with the number of nodes instead of shrinking, that's called Runge's phenomenon. And it's not good. It's not good for Newton-Cotes quadratures. So here's what we do. We say, I can fix Runge's phenomenon by choosing a different node spacing. Instead of choosing evenly spaced nodes that give us this problem, I'm not going to use evenly spaced nodes. I'm going to use Chebyshev nodes of the first kind. So the way we choose Chebyshev nodes of the first kind is that I'm going to place evenly spaced intervals around the circle and then map those points down onto the x-axis, and the resulting node spacing is not going to quite include the endpoints of my interval, but it's going to be a little bit more dense near the endpoints and a little bit more sparse around the middle than you would if you were just having plain linear evenly spacing. And this is going to be better. But remember this. This is Chebyshev nodes of the first kind, and they do not include the endpoints. If you're interested in a formula, you should be. This is the formula. The nodes are going to be the cosine of j plus a half divided by k plus 1. Remember, k plus 1 is the number of nodes in all of our notes. I'm trying to be consistent with that, but k plus 1 is the number of nodes. So it's your index, because we're going to choose a bunch of different j's from 0 to k. plus a half divided by the number of nodes times pi. And we're taking the cosine, right? Because this is in blue the unit circle, and cosine will tell you the x coordinate around the unit circle. And so all I'm doing is when j increases from 0 to 1 to 2 to 3, I'm incrementing the angle. And that's what gives me the evenly spaced nodes around the circle. And then the cosine places those on the x-axis. Okay, good so far? So on the left, I'm going to show you the interpolated polynomial with evenly spaced nodes. On the right, I'm going to show you the interpolated polynomial using Chebyshev nodes of the first kind. Not too much difference when we use 5 nodes. You can already see the difference when I use 7 nodes. And kind of interesting to me is like the evenly spaced nodes are doing a better job around the middle of the interval, but obviously a much worse job near the ends. But you see how this is actually worse around the middle when I use the Chebyshev nodes? And then here's 9 nodes and 11 nodes. But see, the Chebyshev nodes of the first kind are eliminating Runge's phenomenon. It's converging, the orange polynomial is converging towards the blue function more uniformly. You'll end up with the crazy lumps. Connor?
Does that phenomenon happen often? The little side?
With the evenly spaced nodes? Yeah. I mean, this is not the only function where this happens, but you can pick any function as long as it's not a polynomial. Because if you have a polynomial, like I've got a degree 10 polynomial, then a degree 10 interpolated polynomial is the degree 10 polynomial. But if we're talking about an analytic function that has like a infinitely long Taylor series, right? An infinite number of terms in the Taylor series, then yeah, this is subject to happen for sure. Like this function being 1 divided by 25x squared plus 1, that's not a polynomial. So at this point, what we've seen, whenever you look at a graph like this, is we've seen some evidence that the Chebyshev nodes might perform better than the evenly spaced nodes. But as is the case with all math, like we don't just rely on evidence the way that scientists would rely on evidence. We rely on logical proof, right? And so we are now motivated to think, how can I prove that the Chebyshev nodes of the first kind are going to handle our Runge's phenomenon better than evenly spaced nodes? I want to prove this. And this is going to be a long, 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 long process. You can tell I've got 19 pages of notes. So, go grab your coffee, use the restroom. It's going to be a lot. It's going to be a long time before we prove this. Okay, you guys are familiar with this, right? Have you seen the proof for cosine squared plus sine squared equals 1? Really easy thing to prove. If I ask you to do this on a test, what I would like you to do is draw a right triangle with an angle theta and a hypotenuse of 1. Now, this side length is cosine theta. This side length is sine theta. And this follows from the Pythagorean theorem. Quick and easy proof, right? A squared plus b squared equals c squared. And then you remember the definition of cosine is the adjacent side length divided by the hypotenuse, and then the definition of sine is the opposite side length divided by the hypotenuse, so it's perfect. This is an interesting formula. It's one of my favorite proofs in math, and so I maybe even have done this, I think, at some point this semester, because I think on the first day of class, I can't remember who asked me, but some student on the first day of class asked me in one of my classes, what's your favorite proof from math? And so I think I showed this proof. Maybe it was this class, maybe it was a different class. But here's the proof. we're trying to show that e raised to the power I times theta is equal to cosine of theta plus I times sine of theta, where this I is the square root of -1. And here's what you do. You say, I'm going to define a complex number z that is equal to cosine of theta plus I times sine of theta. And so I say z is a complex number because it's got a real part and an imaginary part. If theta is a real number, then cosine of theta is a real number, sine of theta is a real number, so the I times sine theta is the imaginary part of this complex number. And then I ask, what would be the derivative of z with respect to theta, as I've defined it in this formula? What's the derivative of cosine? Negative sine. What's the derivative of sine? Cosine. So we could say that the derivative of z with respect to theta is I times cosine of theta plus I squared times sine of theta. Be consistent with my parentheses. Because what is I squared? -1. And if that's true, I could say the derivative of z with respect to theta is I times z. Because z is cosine of theta plus I sine theta, and if I just multiply both of those terms by I get the derivative here. Now, what I would like to do next is divide both sides by z. So I'll write 1 divided by z times dz d theta is equal to I. And then, to keep my equation balanced, I'm going to take on the left side the antiderivative with respect to theta, and on the right side the antiderivative with respect to theta. Whenever I have the antiderivative of 1 over z dz d theta, this is the same thing as the antiderivative of 1 over z with respect to z. And if I take the antiderivative of 1 over z, that gives me what? The natural log of z plus a constant. What's the antiderivative of I with respect to theta? I theta plus a constant. And of course, I can subtract c1 from both sides, and we'll just say that the natural log of z is equal to I theta plus c. And then, how do I get rid of the natural log? E. So that means z must be equal to e raised to the power I theta plus c. And all that is left for us to do is to figure out what is the value of lowercase c. What I know is z, as we defined it in the beginning, is cosine of theta plus I sine of theta. And so what would be z if I set theta equal to 0? Then z would be cosine of 0, 1. plus I times what's sine of 0?
0.
0. So z needs to be equal to 0 when, sorry, let me say that again. Z needs to be equal to 1 when theta is equal to 0. Obviously, I times 0 is just 0, so this needs to be equal to 1, right? So what does my little lowercase c need to be equal to?
0.
Yeah. In order to make e raised to the power c equal to 1, the only value of c that works is c equals 0. So e to the power 0 is 1. And then I combine this with this to decide that, well, this z, which is equal to e to the power I theta, is also equal to cosine of theta plus I sine theta. The right side of this equation is the definition that we started with, and the left side of the equation is what we found through that proof. This is called Euler's formula, and I really, really like this proof personally because I think it's easy to remember. You know, whenever I memorize a proof, I'm not memorizing every single step in the proof. Whenever I memorize a proof, I just remember, like, what are the big decision points, right? The first decision point is writing z equals the right side of Euler's formula. The next thing to remember is I need to take the derivative. The next thing to remember is that the derivative should eventually look like I times z. And the next thing to remember is I'm going to take an antiderivative with respect to theta. And then I don't have to remember anything after that because you can just work through it, you know? So there's only a few, maybe 3 or 4 decision points that you have to remember in order to memorize a whole proof like this. But did that make sense? Have questions? Okay. So every complex number can be represented in a polar form. A complex number is a number with a real part plus an imaginary part. So in this case, x would be my real part, and I would be my imaginary part. And the whole thing is called a complex number, and this is what we would call standard form. And this is what we call polar form. The polar form comes about because e to the I theta is the same thing as cosine theta plus I sine theta. So I get r cosine theta plus r sine theta times I. And so once again, this is my real part, and this is my imaginary part. So I could say, for example, if I wanted to convert this back to a standard form, I get the x coordinate by r cosine theta, and I get the y coordinate, or the imaginary part, by r sine theta. Which should remind you of polar coordinates. And if I want to convert from standard form to polar form, then this r is going to be equal to the square root of x squared plus y squared. Because this r is going to be the distance from 0 to z in the complex plane. R is also the absolute value of a complex number. So whenever we talk about complex numbers, we imagine them living in a plane where this is my real axis, and that's like the real number line, and this is my imaginary axis, which is like an imaginary number line. And every point, every complex number, belongs to the plane somewhere. And so if I wanted to measure the distance from the origin to this point, that would be r. And that would be the absolute value of this complex number. Then theta is this angle that's measured counterclockwise from the positive x-axis. And if I wanted to write this in standard form, I would write something like -4 plus 3i, where -4 would be the real component and plus 3i would be the imaginary component. That would put me right there on the plane. Or I could give you the r and the theta, the distance from the origin and the direction we're pointing, to come up with the same complex number. So converting from standard form to polar form means calculating r as the distance, the square root of x squared plus y squared, and then theta is such that tangent of theta would be equal to y divided by x. Because remember, tangent is sine divided by cosine. And in the plane here, sine of theta would be the vertical, and then cosine of theta would be the horizontal. It was in a different class. It was in Calculus 3 where I really spent a lot of time explaining why it's difficult to take the arctangent. It's difficult to take the arctangent like this. I could define theta equals arctangent of y divided by x. Aaron, do you remember why it's difficult to take the arctangent?
Because of the quadrant issue.
The quadrant issue. The arctangent works as long as my complex number is in the first quadrant or the fourth quadrant. The arctangent works really well. But if I have a theta or a complex number that ends up in the third quadrant, then my real part is negative and my imaginary part is negative, right? So y is negative and x is negative. But a negative divided by a negative is a positive. And so these points in the third quadrant are indistinguishable from the points in the first quadrant. When I plug them into the arctangent function, it's the same argument, whether you're in the first or the third quadrant. And the same thing for the second quadrant. The second quadrant is overlooked because those points are indistinguishable from the fourth quadrant. Because in the second quadrant, the real part is negative, the imaginary part is positive, and so I've got positive divided by negative is negative. And then over here in the fourth quadrant, the real part is positive, the imaginary part is negative, and I still have negative divided by positive, so I still have a negative argument, and you can't tell the difference. And so if you have a complex number in the second or third quadrants, if you've got a complex number in the second or third quadrants, then all you need to do to get the right answer is add pi. Because that will move you from the first quadrant to the third or the fourth quadrant to the second. So this plus pi is if z is in the second or third quadrant. Okay, but that's how you convert between the two. Questions about that? About converting a complex number from standard form to polar form? You see how every standard form can be represented in polar form, and every polar form can be represented in standard form. So the next question is, what would it mean geometrically to multiply two complex numbers? Well, let's say I have a number z1, and it has coordinates r1, theta 1. And I have a number z2, which has coordinates r2, theta 2. what would it look like to have z1 times z2? I could write r1, r2 times e raised to the power I times what?
Theta 1 plus theta 2.
There you go. So Connor remembers his properties of exponents. So the product has an absolute value, right? Let's call the product z3. Why not? That's the absolute value of z1 times the absolute value of z2. Because remember, that's just the r coordinate in polar coordinates, right? And the product also has theta 3 equal to theta 1 plus theta 2. Right? So whenever I ask what would it mean geometrically to multiply two complex numbers, what I'm looking for in this answer is to say, I'm actually adding the angles together. I'm adding the angle measured counterclockwise from the positive x-axis when I come up with the product. So let me give you a little example. I'll draw you a picture. Here's my complex plane with the real and imaginary axes. And let's say here's a point with an absolute value of 1 and a theta of pi over 4, let's say. Here's another point with an absolute value of 2 and a theta of pi. So this is just the number -2. Then what if I wanted to multiply these two together? What if I want to multiply this number, which would be like square root 2 over 2 plus square root 2 over 2i times this number, which is -2. Well, then I would add these thetas together. This is theta 1. This is theta 2. And so whenever I multiply them, the product is going to have an angle of 5 pi over 4. And then the absolute value of this is 1, the absolute value of that is 2, so the absolute value of this is also going to be 2. You multiply the absolute values, but you add the angles to get the products of complex numbers. The important part I want you to remember right now for lecture is remember that when you multiply two complex numbers, you are adding the angles together to get the angle of the product. This is the most important part that I want you to remember. Okay, so what if I have this? It's a standard trigonometry theorem. It's the angle sum formula for cosine. Maybe you've seen this proof before, maybe you haven't. But the proof goes like this. It says, on the one hand, let's consider e raised to the power I times alpha times e raised to the power I beta and on the other hand, let's consider e raised to the power I times alpha plus beta in parentheses like that. So we know that's true. That's just a property of exponents. And then we use Euler's formula. On the left side, Euler's formula is going to give me cosine of alpha plus beta plus I times sine of alpha plus beta. On the right side of the equation, Euler's formula is going to give me cosine of alpha plus I sine beta, I sine alpha, my bad, times cosine of beta plus I sine beta. Do we agree so far? Yeah? Okay, so what we're going to do is we're going to FOIL the right side of this equation. And that would give me cosine alpha, cosine beta, plus I times sine beta cosine alpha, plus I sine alpha cosine beta, minus sine alpha sine beta. Why did I write minus? Where did the minus come from? Yes, I squared is -1. So all we're left to do is to equate the real parts of the left side and the right side. And we get the exact trig identity that we're trying to prove here. Cosine alpha cosine beta minus sine alpha sine beta. If you equate the imaginary parts on the left and right side of the equation, then you get the angle sum identity for sine. But Euler's formula is kind of like the mother of all trig identities. You can prove any trig identity you want using Euler's formula. Just plug different things in for the theta. In this case, instead of e to the I theta, I used e to the I alpha plus beta. But you can plug anything you want in there and it will give you a different trig identity. Basically, all of them are proved, including this one. Like, if I want to prove this double angle identity for cosine, what I'm going to do is I'm going to start with e to the power I 2 theta instead. Right? Cosine of 2 theta? E to the I 2 theta. That's how you figure out how to start one of these proofs. All trig proofs start the same. And then on the right side, I'm going to remember a property of exponents that says e to the I 2 theta is equal to e to the I theta raised to the power Yeah, you remember that one? Okay, you guys don't look comfortable. Let's try to convince you. If I have x to the power 2 raised to the power 3, that would be x times x times x times x times x times x, right? X squared times x squared times x squared. That's x to the power 6. And that's not a coincidence, right? 2 times 3 is 6, but it's because I've got 2 copies of x 3 times, so 6 total copies of x. Same thing is happening here in purple. Now on the left side, let's apply Euler's formula. On the left side, we're going to get cosine of 2 theta plus I sine of 2 theta. And on the right side, I'm going to get cosine of theta plus I sine theta squared. And now just like with the previous proof, after we apply Euler's formula, we're going to FOIL the right side of the equation. When I FOIL the right side of the equation, I get cosine squared. First outer inner is going to be plus 2I cosine theta sine theta. And then last is minus sine squared theta. Why did I write a minus sign? Where did the minus come from? I times I. I squared is -1, so that's where the minus comes from. And then all I have to do is equate the real part on the left side to the real part on the right side. And now I can write that cosine of 2 theta is equal to cosine squared theta minus sine squared theta. That's a common trig identity, the double angle identity for cosine. If I underline the imaginary part on the left side and the imaginary part on the right side, I get a double angle identity for sine. That's equally useful. Now, that's not exactly the theorem I'm trying to prove, is it? To get to this part, I also need that nice identity that says cosine squared plus sine squared is equal to 1. Because that means cosine squared theta minus 1 is negative sine squared theta. Now let me substitute that in here. And that gives me cosine 2 theta equals, and then I end up with 2 copies of the cosine squared minus 1. Feel good about that? Cool. Did you guys do this in your trig class? You did? No? Okay. I've never taught trigonometry before, so I don't know what you actually do in trigonometry. I'm just taking guesses.
Yeah,
Trying to.
class we did proofs.
That's good. So what does this say? Natural number powers of complex numbers. So if I take that complex number z and I raise it to the power 3, I raise z to the power 5 or whatever, what does it do? Specifically, we're thinking about complex numbers that have an absolute value of 1. So if the absolute value is 1, that means in the polar form, r is equal to 1, and that means z is equal to e to the I theta. That's a complex number with absolute value 1. And if I take a natural number of power of that, it's going to yield the sum of a real polynomial of cosine and an imaginary polynomial of sine. And I've already done some of the work here in where it's typed up, but you can kind of see what I'm talking about. If this is absolute value 1, it looks like e to the I theta. So I've got e to the I theta raised to the power n, and that's Euler's formula, right? Raised to the power n. Alternatively, I could use that property of exponents to bring the n down and make it e to the power I times n theta. And then Euler's formula applied to this looks like cosine of n theta plus I sine n theta. And these two things should be equal to each other, right? So we set those equal to each other. And now notice, the real part on the right-hand side of this equation would start off with cosine theta raised to the n power. And then, yeah, there's definitely going to be some times where we end up with an imaginary term that includes like I sine theta times some powers of cosine. But there's also going to be some real terms in there that involve like times when I choose the I sine theta factor an even number of times, because if I multiply I sine theta times I sine theta, it gives me I squared sine squared theta. Right? So I don't know how to write this. I know how to explain it kind of, but not sure how to write this. If k is an integer, then 2k is an even integer. And that would also be real, right? Because I to an even power is either 1 or -1. And then I end up with an even power of sine. And there could be many of these terms, right? Depending on what that lowercase n is. There could be a lot of stuff going on there. But every term in the expanded version of the right side of this last equation is going to look like an imaginary term, because it has an I in front of it, or it's going to have cosines times an even power of sine. So what do we do if we have an even power of sine? Well, even powers of sine can be turned into cosines. Like, for example, I'll show you. If I were talking about cosine of 3 theta, why not? This would be cosine of theta plus I sine theta raised to the power 3. And so the right side of the equation would expand as cosine theta cube plus there are 3 ways to pick I sine theta cosine squared theta. And there are 3 ways to pick out I squared sine squared theta cosine theta. And then there's 1 way that you get I cube sine cube theta. Now, we're going to ignore all of the imaginary parts, okay? And we get cosine of 3 theta is equal to cosine theta cube plus -3 sine squared theta cosine theta. But what specifically I want, what my theorem is telling me is that cosine of n theta, like cosine of 3 theta, should be a degree 3 polynomial of cosine. That's the part I'm trying to prove right now, okay? This is what I really, really care about. This is what's important to the next step in our lecture, as I care about this part. So I'm trying to show you that cosine of 3 theta is a degree 3 polynomial of cosine theta. And all I need to do here is replace sine squared with what?
Cosine squared minus 1.
Oh, you're really close. That's the Pythagorean theorem, right? So 1 minus cosine squared theta. And that means I can write cosine theta cubed plus 2 negatives make a positive, so it's 3 cosine theta cubed minus 3 cosine theta. Combine that, and it's 4 cosine theta cubed minus 3 cosine theta. So this is looking like a degree 3 polynomial, right? It's just a degree 3 polynomial of cosine theta. That's what I'm trying to tell you. And I just showed you an example of what it looks like with n equals 3, but the idea is no matter what n you choose, this right side expansion is always only going to contain imaginary terms, or obviously the first term is just going to be real and it's going to be cosine, or it's going to contain terms that have an even power of sine, and we can turn even powers of sines into cosines by writing them as 1 minus cosine squared, right? So that's the idea. That's the trick that makes all of this happen. So we're convinced. Now, you finally get to learn what a Chebyshev polynomial is. Ben's excited. The Chebyshev polynomials are the set of, and there's infinitely many polynomials. There's a Chebyshev polynomial of every degree. There's a degree 0, degree 1, degree 2, degree 3 Chebyshev polynomial. But this is how they're defined. It's a polynomial of cosine theta that is equal to cosine of n theta. The lowercase n is the degree of the Chebyshev polynomial. And what we just did in the previous theorem, what I was trying to convince you of, that cosine n theta is a degree n polynomial of cosine theta, we just proved that these exist. So now we can feel comfortable with the idea of making this definition because we know that these exist. Let me show you what it looks like. I've got a Desmos ready, I think. Not on Edge. I need to load this on Chrome. And we are in numerical analysis. Here we go. So, what are we looking at? Show you one thing at a time. It's a little bit less busy. In orange, this is the degree 0 Chebyshev polynomial, because if I set n equal to 0, we're talking about cosine of 0, which is just 1. What if I want to show you the degree 1 Chebyshev polynomial? So I'm going to change n from 0 to 1, and boom, there's my degree 1 Chebyshev polynomial. What if I want the degree 2 Chebyshev polynomial? The degree 2 Chebyshev polynomial is 2x squared minus 1, by the way. You don't need to know that, but that's what it is. So in green, that's my degree 2 Chebyshev polynomial, and I can get there if I change n from 1 to 2. Boop. And then my degree 3 Chebyshev polynomial is 4x cubed minus 3x. Hey, we actually found that, right? 4x cubed minus 3x. We found the degree 3 Chebyshev polynomial a second ago. But I'm going to show you that. That's in purple now. And if I change n from 2 to 3, I can make it match the degree 3 Chebyshev polynomial. And then here's my degree 4 Chebyshev polynomial, 8x to the 4th minus 8x squared plus 1. And then I'm going to change n from 3 to 4. And there you have it. Okay, I thought that was cool. Okay, the n roots of the Chebyshev polynomial Tn, because it's degree n, it should have n roots, are exactly the Chebyshev nodes of the first kind. Remember, when we were placing nodes evenly around the circle and then we mapped them down to the x-axis, those are the roots of a Chebyshev polynomial. We can prove this pretty quickly. The proof is we write down the definition of the Chebyshev polynomial, and then where I'm going to plug in where the roots should go, I'm plugging in the formula that I gave you for the Chebyshev nodes of the first kind. But since I have Tn of cosine of theta, in this case Tn of cosine of this whole thing, I can replace that with cosine of n times theta, so I get cosine of n times this whole thing. The n's cancel, don't they? And then I get cosine of an integer, 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever, an integer times pi plus pi over 2, and cosine is 0 at every integer multiple of pi plus pi over 2, isn't it? So those are the zeros of my Chebyshev polynomial. They happen at the Chebyshev nodes of the first kind. We can also write a recurrence relation that makes it really easy to calculate what the next Chebyshev polynomial will be. If you remember that the first one is the degree 0 Chebyshev is just equal to 1, and the degree 1 Chebyshev polynomial is just equal to x, then every other one can be determined by this recurrence relation. So if I want to prove this, we are going to begin your proof just by verifying that, from my definition of Chebyshev polynomial, that this works. When n is equal to 0, cosine of 0 is 1, and so my polynomial should be 1. And then, what happens when n is equal to 1? Well, the polynomial should just be x, because what it should be equal to is cosine of theta. So you compose those and you just get it. So what about the rest? To establish the recurrence relationship, remember this angle sum identity of cosine? And then what I want to do is say this is equal to cosine of n theta plus theta. And that is equal to cosine of n theta times cosine of theta minus sine of n theta sine of theta. Well, what about this? This is cosine of n theta minus theta, also known as plus negative theta, which is cosine of n theta times cosine of negative theta. Did you know cosine is an even function? Which means that cosine of negative theta is the same thing as cosine positive theta. It doesn't matter whether the argument is negative or positive, you get the same value of cosine because it's symmetric about the y-axis. Anyways, we use that fact here. And then what else? Minus sine of n theta sine of negative theta. By the way, did you know that sine is an odd function? So that sine of negative theta is equal to negative sine of theta. I'm using that fact here to change that negative to a positive. And so what I would like to do is add these together, because this is cosine of n theta, right? And so Tn plus 1 of cosine theta is equal to cosine of n plus 1 times theta, and Tn minus 1 of cosine theta is going to be equal to cosine of n minus 1 times theta. And so this is saying what I'm going to do is I'm going to subtract the two. No, add the two. I'm going to add these. And when I add these together, notice the first term is exactly the same. And so when I add those two together, I'm still going to get 2 cosine n theta cosine theta. When I add the next two terms, one of them's negative, one of them's positive. Otherwise, they're exactly the same, so those go away. Now look at what I'm trying to prove here. Take a look back at this, the part that I'm trying to prove. And let's start to try to piece it together here. On the left side of the equation, I've got this Tn plus 1, which is this first bit. X is cosine theta, right? And then on the right side of the equation, I've got this minus Tn minus 1. Let's make that plus Tn minus 1. And then the right side would be 2x Tn of x. And what I just did is I just added Tn plus 1 and Tn minus 1 together. And so that is the left side of the equation. Two cosine theta cosine n theta. And that's supposed to be equal to 2x Tn of x. Remember, x is cosine theta, right? So it works. Sorry, I've got arrows all over the place. But right here, you've got every little piece you need to piece the puzzle together, right? Do you like it better when I type out the proof, or do you like it better when I just write it down? Because it depends, right? So this is a tricky thing to come across. But once you discover this recurrence relation, this is an easy way to calculate the Chebyshev polynomials versus like starting from Euler's formula every time. You end up doing a lot less work if you just know this recurrence relation. So we've got a few more minutes left. The next thing I want to explain to you or kind of convince you of is that the leading coefficient of the degree n Chebyshev polynomial is 2 to the power n minus 1. So if the degree of my polynomial is n, the leading coefficient is 2 to the power n minus 1. And that's because the degree 0 polynomial is 1, the degree 1 polynomial is x, and the degree n plus 1 polynomial is 2x times the degree n polynomial minus the degree n minus 1 polynomial, right? Is that the recurrence relation? Yeah. So let's keep a little tally of degree and leading coefficient. When the degree is 0, the leading coefficient is 1. When the degree is 1, the leading coefficient is 1. It's 1x, right? And then when the degree is 2, this formula is saying take the degree n polynomial, multiply by x, which will make it an n plus 1 degree polynomial, and then you multiply by 2. So now the leading coefficient gets doubled, and the leading coefficient is 2. And whenever I increase the degree again, the leading coefficient gets doubled, so it should be 4. And then it doubles every time according to this recurrence relation. And so when you get to degree n, the leading coefficient is going to be 2 raised to the power n minus 1. Because like 4, if n is equal to 4, it's not 2 to the power 4, it's just 2 to the power 3, right? It's always 1 less than the degree. Okay. Finally, we're at the point where we can prove what we set out trying to prove. What we wanted to prove, remember, was that like these Chebyshev nodes of the first kind were going to minimize Runge's phenomenon. We wanted to minimize the big crazy spikes that we get at the edge of the intervals when we use evenly spaced nodes. And what better way to do that than try to choose nodes that would minimize the maximum absolute error over any x inside the interval. So like this, what I'm showing you here, would be the maximum absolute error of x for a point x inside the interval. And we've already kind of seen some evidence that the Chebyshev nodes of the first time do this, but this time we're going to come up with a proof now that we've kind of developed all of the background to do this proof. So we're making the claim that the Chebyshev nodes of the first kind minimize the maximum absolute error of the Lagrange interpolating polynomial on the interval from -1 to 1. In other words, when you're given k plus 1 nodes to place in that interval, the Chebyshev node placement will result in the value of the constant, the maximum of the absolute value of the error for x values inside the interval from a to b that is less than any other possible node placement. A and b are supposed to be -1 and 1 for this lecture. So let's keep that in mind. If you see a and b, assume that's -1 and 1. We can generalize this later in the week, but for now, we're just talking about the interval from -1 to 1. So in the proof, we start off by considering that formula that we love so much that tells us the error of the Lagrange interpolating polynomial we found in a previous lecture, right? The big scary formula. This leading factor that contains the k plus 1th derivative of the function, that's a constant, it doesn't matter. K plus 1 factorial, that's a constant, it doesn't matter. The only thing that depends on the node spacing is the product, because these xi's are the nodes. So this is the part that we actually have control over. we don't have any control over the function that we're trying to interpolate. And we're saying we're given k plus 1 nodes to place. We don't have any choice of the k plus 1 factorial, but what we do have control over is the nodes. So we're really just trying to minimize the stuff that I circled in orange. The Chebyshev polynomial that has degree k plus 1 will have a leading coefficient of 2 to the k. So we are going to invent a polynomial lowercase p, and it's the same thing as the Chebyshev polynomial of degree k plus 1, but this time I'm multiplying by 1 divided by 2 to the k, because that is going to make it a monic polynomial. If you haven't heard the word monic before, monic means it has a leading coefficient of 1. So this is going to be what's called a proof by contradiction. My claim is that among all monic polynomials of degree k plus 1, lowercase p is the one that has the minimum value of the maximum of the absolute value of the polynomial. Proving by contradiction means this. I'm going to suppose that my claim is not true to begin with, and then at the end I'll tell you that, yeah, we just found a contradiction, which means my claim has to be true, right? So suppose my claim is false, and that means suppose there exists a polynomial q, which is a different monic polynomial that has a smaller value of that maximum. So that way, the maximum of the absolute value of q over all of the x in the interval from -1 to 1 is less than the max of p. We define a new function. My new function is g of x, and that's going to be 2 to the power k times q, my new polynomial that we made up, minus the Chebyshev polynomial of degree k plus 1. G has to be a polynomial because it's one polynomial minus another polynomial, right? And the degree has to be at most k. Because q is a polynomial with degree k plus 1 and a leading coefficient of 2 to the k, p is a polynomial with degree k plus 1 and leading coefficient 2 to the k. So when I subtract them, their leading terms are the same, and their leading terms are going to cancel each other out. So if the x to the power k plus 1 terms cancel each other out, the next biggest power of x would be k. Does that make sense? Now, we know the Chebyshev polynomial has k plus 2 extreme values, and this is where they occur. Because the Chebyshev polynomial, it's going to be equal to cosine of n theta, which means that it's going to oscillate the way that cosine does. And using that logic, we can find the extreme values on the interval from x equals -1 to x equals 1. At the endpoints, right? So on this red curve, there's extreme values at the endpoints and at all the stationary points. And since it's a cosine function, the stationary points are going to be zeros of the sine function, sine of n, whatever. But that's it. Notice that in red, this is a degree 4 Chebyshev polynomial. And there's actually 5 extreme values, right? There's the 2 that are at the endpoints. And then when I take the derivative of a polynomial, it decreases in degree by 1. So the derivative is going to have degree 3. So that means the derivative has 3 zeros, and that means the polynomial has 3 stationary points. So I've got 2 extremes on the endpoints, and then k extreme values at the stationary points. And all of these extreme values are going to be either 1 or -1. That's important too, right? Because this is a cosine function. The max I can get out of cosine is 1. The minimum I can get out of cosine is -1. And so the values are all 1 or -1. That's what I say next. These extreme values are all plus or minus 1 with alternating signs. And so at each of these extreme values, we're going to have this formula for my g function. Just take this, plug in the extreme values, and since the Chebyshev polynomial is either +1 or -1 there, that's the replacement that happens. And this is the main idea. I realize I have 2 minutes left in lecture, so I'm going to quickly gloss over this. Capital M is going to be the maximum of that Q function. Remember that maximum is supposed to be less than the max of P. The max of P is going to be 1. No, sorry, that's a typo. I'm glad I found that typo though. So, right, because we're dividing, P is equal to 1 divided by 2 raised to the power k. So that should be 2 to the -k. Perfect. That's good. So I fixed my typo. Glad we fixed the typo. But that means whenever m is even, you look at this formula and an even m makes this a +1, so I'm subtracting a +1. And when m is odd, I get the opposite. So I'd be subtracting a -1 or adding a 1. That g function is going to alternate plus or minus signs at the extreme values of your Chebyshev polynomial. When it switches from positive to negative, it has to go through 0. This is a continuous function, so the intermediate value theorem applies, and it has to go through 0 as it goes from positive to negative or negative to positive. And so whenever I switch plus or minus signs, that tells me I've got a 0. And so if it's switching plus or minus signs, that means g has at least k plus 1 distinct zeros, but that means it's a degree k plus 1 polynomial. And in fact, we just showed earlier that this has to be a degree k or less polynomial, which is a contradiction. So that's the contradiction we're trying to find. That means my original claim has to be true. If my original claim is true, and we notice that this lowercase p polynomial that I defined is actually the same thing as this big product here, then choosing the Chebyshev nodes of the first kind as the node spacing is going to make this monic polynomial equal to the monic polynomial that has the smallest maximum absolute error on the interval. And so that's what minimizes this. And I can also tell that this interpolating polynomial is going to converge to the function if I make k large enough, because this monic polynomial has an absolute maximum error. Well, we've got Chebyshev nodes of the first kind. Now let's talk about Chebyshev nodes of the second kind. And this looks like a really similar picture, except look, this time we're putting points at -1 and 1. We're including the endpoints of the interval. Other than that, I'm still evenly spacing the nodes around the circle and aligning them vertically. But Chebyshev nodes of the second kind include the endpoints when you do this. If you want the Chebyshev nodes of the first kind, you take the circle and you rotate it just a little bit. So that way the endpoints get off. And the second kind, you put the endpoints back on the circle. So that's the difference. The formula looks pretty similar, but not exactly the same. The only difference you'll notice, when we had Chebyshev nodes of the first kind, this numerator was j plus a half divided by k plus 1, and this time it's just j, because whenever I start j at 0, then I'm taking cosine of 0, which gives me this node right here at 1. But whenever I have Chebyshev nodes of the first kind, I don't want a node to be sitting there at 1. So I add the half to make it offset by a little bit. Okay. The next new vocabulary term is the word nesting. Evenly spaced nodes are nesting. And what I mean by that is this. If I were to draw you some evenly spaced nodes on this interval, here's 3 evenly spaced nodes. So this would be like a Simpson's rule nodes. If I want to bump this up and get 5 evenly spaced nodes, I get to keep the 3 evenly spaced nodes I used for Simpson's rule. And then I just add 2 extra nodes to get my Boole's rule nodes, right? So when I say they're nesting, I mean if I want to increase the degree of exactness, I don't have to find a whole new set of nodes. I just use the ones I have and then I add a couple. So on the left, I've got Chebyshev nodes of the first kind. And on the right, I've got Chebyshev nodes of the second kind. Notice the Chebyshev nodes of the first kind are not nesting. Whenever I double the number of nodes from here to here, I put little orange X's where the nodes used to be whenever I only had 4 nodes, right? Going from 4 to 8, these are where the 4 were, and they don't belong to the set of 8. But if I look at Chebyshev nodes of the second kind, here I'm going from 5 nodes to 9 nodes. And I put them in green, but you can see where the original 5 nodes were. No, sorry, I lied. I put them in black, right? These 5 black dots are the 5 black dots here. They're the same nodes. I'm just adding in 4 new nodes in between them. So we say that the Chebyshev nodes of the second kind are nesting, and that's a good thing. We want nodes that nest so that we can keep them when we develop a bigger set of nodes. Another thing you should notice is that what are the green dots? The green dots here in this picture are actually these Chebyshev nodes of the first kind. So when I have 4 Chebyshev nodes of the first kind, they fit in between these 5 Chebyshev nodes of the second kind to give me 9 Chebyshev nodes of the second kind. So the second kind is nesting, and also the second kind includes nodes of the first kind of a lower order. Whereas the first kind, they're not even nesting. So, some things we might be concerned about. Are the node locations easy to calculate? I would argue that all 3 of these are easy to calculate, because if you're just going to make a Python script, right, you can just program this in as one line in a Python script. It's an explicit formula for the node, so I would say yes, yes, yes. Those are all easy to calculate. Are they nesting? Well, evenly spaced and second kind are nesting, first kind are not. That makes us sad. And we already saw for Runge's phenomenon, the evenly spaced nodes cause a problem. The error just actually increases and increases when I increase the number of nodes. We saw with proof that Chebyshev nodes of the first kind are the optimal choice to minimize Runge's phenomenon. And what we'll find is that with Chebyshev nodes of the second kind, it's not as good as the first kind in dealing with those errors, right? Because the first kind is optimal. These are not optimal. But because the second kind includes the nodes of the first kind, you know, of a lower order, and because you're still using the same overall circular density pattern, right? It's still more sparse in the middle because the circle is flatter, and it's still more dense on the edges because the circle gets steeper. You're still using the same overall kind of scheme. Now you get pretty close to the same level of control over that Runge's phenomenon error. So it's not optimal, but it's still pretty darn good. And so you can already see why we might start to favor these nodes of the second kind, because even though it's not optimal, it's still pretty good, and this is a big benefit, being able to have nesting nodes.